Hello, my name is Diana Chan, and I'm a chemistry tutor at the Natural Social Science Lab at MDC Kendall campus. Today I'm going to discuss atomic weights, isotopic abundances, and their relationships to isotopes in this video. First, we'll discuss how to recognize the atomic number Z and the mass number M, so that you may identify an isotope when you see one. As a quick reminder, subatomic particles to note are protons, subatomic particles that have a mass and a positive charge; neutrons, subatomic particles that have a mass but exhibit no charge; and electrons, subatomic particles that do not have a mass and has a negative charge. Put simply, the atomic number is the number of protons an element has. This number is stapled to the element. If you change the number of protons, you are essentially changing the element. We can identify the protons, or the atomic number, by looking at our handy periodic table. I have supplied one for your convenience, but I suggest that you get one yourself to practice with. Looking on the periodic table, you can differentiate the proton number because it will be the whole number associated with each element. And I have kind of circled these atomic numbers for you to show you. They are, on this periodic table, the number on the top. This makes sense, right? Because, for example, you can either have 4 or 5 protons. 4 protons would make it beryllium, and 5 protons would make it boron. And I'll just show that to you with my little snippet of the periodic table. Beryllium has 4 and boron has 5. But for example, you can't have 4.5 protons. As you can see here, there are no elements with 4.5 protons. This makes sense because protons only exist in whole numbers. You can't have half of a proton. As a general custom, the atomic number will be labeled Z. Mass number, put simply, is the weight of the element in either AMUs per atom or grams per mole. The mass number is the sum of the protons and neutrons an atom has. This number is easily identified as the number, the non-whole number associated with each element. And I'm going to highlight again it for you. As you can see, there are all these little decimal points associated with each of these elements. And on this table, it sits on the bottom of the element. Now, let's think about this. If the mass number is equal to the sum of the protons plus the neutrons, and both the protons and the neutrons are both whole numbers, how is it that the mass number is not a whole number? The reason for this is because although the mass number is an addition of whole number sums, they are also the average of all of these sums. For example, when determining carbon's mass number of 12.011, researchers looked for the average weight of carbon. How they did this was that they grabbed mole samples of carbon and weighed them, and on average they equaled 12.011 grams per mole. Some of them weighed less than 12 grams per mole, some of them weighed more than 12 grams per mole, but on average each mole weighed 12.011 grams. Whereas a proton defines an element and cannot be changed, a mass number can vary tremendously between and within each element. The reason for this is because although your protons, or your number of protons, or your atomic number, cannot change without changing the element itself, the neutrons can vary tremendously. Remember that our mass number is equal to our protons plus our neutrons. Consequently, if your protons don't change, but your neutrons do change, so do your mass number. This is defined as an isotope. An isotope is a variation of an element existing with the same number of protons, but a different number of neutrons, and therefore a different mass number. Now that we know the definitions, we can use this information to solve problems regarding average atomic weights and their isotopic abundances. Now, here is the formula from Module 5, where the average atomic weight is equal to fraction 1 times atomic weight 1 plus fraction 2 times atomic weight 2. And underneath here, I've kind of defined these variables where average atomic weight is usually equal to the number you see on the periodic table. So that would be your mass number, M, or your molar mass, or your AMUs per atom. F1 is equal to the fraction or the percent of isotope 1. Atomic weight 1 is equal to the atomic weight of isotope 1. Fraction 2 is equal to the fraction or the percent of isotope 2. And the AW2 is equal to atomic weight or mass of isotope 2. Another formula given to you in Module 5 is a relationship between the two fractions. We know from Module 5 that the fraction or the percentage 1 plus percentage 2 is equal to 100%, or the fraction of 1 plus the fraction of 2 needs to equal 1. Now, for it to be in this formula, you need to make sure that it is in the percentage form. And for you to be in this formula, the F1 and F2 needs to be in either decimals given, like, for example, 0.50 plus 0.50 equals 1, or in fraction form, 50 over 100 plus 50 over 100 equals 1.0. Now, to let you know, I, as a personal preference, prefer to do it as a decimal form, just because it allows for me to skip a step later on when I have to convert 50 over 100 to 0.5 later on. So I just automatically convert most of my fractions into decimal form to save me a couple steps, just in case I forget, so I don't multiply my atomic weights by, let's say, 50 and end up 2 decimal places off. Because we know that the atomic weight or molar mass of the molar mass is the weighted average mass of all naturally occurring isotopes of that element, we can calculate the average atomic mass from the percent abundances of naturally occurring isotopes. In these next couple of videos, we're going to go over some example problems that just kind of show the different types of problems your teacher could throw at you and how to tackle each different type of problem. I hope that the videos serve you well, and that although they are in-depth, you get a lot of information out of it. So I will see you in the next video with our first example, where we will tackle how to solve for the average atomic weight of an element using the formulas given above and the topics discussed in this past video. So, see you.